Well, good morning and good afternoon in the Far East. My name is Mike Dillon. I'm Vice President of Business Development with CR Wall, and on behalf of CR Wall and Foothills Industrial Products, the CR Wall company, and of course Ionix Gas Technologies, we'd like to welcome you to our webinar today titled "What Causes Pinhole Leaks in PE Gas Service Pipe?" And now it's my pleasure to introduce our presenter and subject matter expert, Dirk Smith. Dirk is president of Ionix Gas Technologies. Ionix specializes solely in static mitigation systems for natural gas distributors. Mr. Smith graduated from the Wharton School of Finance and Commerce at University of Pennsylvania and holds 3 US patents on static elimination technology. He has written numerous articles about static electricity and gas pipelines, which have been published in Pipeline and Gas Journal. We have known and worked with Dirk for many years and can attest to his depth of knowledge and passion for this subject. And we're sure you're going to learn a lot today. Dirk has asked that we hold all the questions until the end, and we will be using the Q&A feature to capture them. Please enter your questions at any time during the presentation, and we'll read them out and respond in order during the QA. With that, Dirk, I'll turn it over to you. Thank you.
Mike, thank you very much, and thank you for CR Wall for sponsoring this webinar on what causes pinhole leaks in PE service pipe. Now, the first question I always get asked, I'm down here in Boca Raton, Florida, so the first question I always get asked is, what's the weather down here today? So this is about 3 miles from my house. You see this timestamp on it this morning at 10:30 Eastern time. So just so you know, that's the weather here. It's about 80 degrees, so you don't have to chat that question in here. Okay, with the essentials being taken care of, then let's talk about the agenda. What we're going to do today is we're going to talk about the researched physics. We're going to go through the researched physics done by the Gas Research Institute on what causes pinholes in PE pipe. This has been paid research by by LDC companies done by the Gas Research Institute. Then next, we're going to move into failure analysis. We're going to go through four failure analysis of previously investigated pinhole leaks in pipe. And we're going to see some patterns emerging in this, and hopefully you'll find them applicable to you. Now, the third thing we're going to do is down here in the States, PHMSA's jurisdiction over PE gas pipe, they recently passed a rule about no regrind in polyethylene pipe. Now, you've had a no regrind rule up in Canada, and I'm not interested in looking at this solely for the rulemaking because it doesn't apply to you. But it's interesting to see the thought pattern of the regulators and the reasoning and the reports and the research they used to make this rule about no regrind, because it implies it has implications directly in pinhole creation and then also your leak management. And then finally, we're going to talk about field test results in preventing pinhole leaks. And so that's the agenda before us. Now, the first thing we've got to do is make sure that everybody we understand the terminology I'm using. Now, we've called this a pinhole leak, and that's really a misnomer. The proper term is it's an electrostatic pinhole, because I'm kind of giving you the end of the story before I tell you the story. But what happens is pinhole leaks are only caused by static electricity. And the Gas Research Institute documented this when they started their initial research on it. And here's their quotation out of their report 920460. And they said, what happens is a charge builds up, electric charge builds up on the inside of the pipe, and it gets so high that it exceeds the material breakdown capacity of the material. And when it breaks down, the electrical charge going through the wall creates heat. And that heat burns the plastic and creates a pinhole. So when you say a pinhole, it really is an electrostatic pinhole. Now, I'll qualify that. You'll understand what the difference is between a manufacturing defect and an electrostatic pinhole later. But that's what the research has said. All pinholes are essentially caused by static electricity, not a manufacturing defect. But then we'll go through that and you'll see that becomes pretty obvious. This is just an illustration, a simple illustration of a piece of buried pipe in the ground of what occurs with what Gas Research just explained. And that is that you see, for some reason, and we'll talk about this later, but for some reason, electrons get separated from molecules and they accumulate at random places inside the pipe. And when the charge gets high enough, it arcs through the wall to ground. They want to ground themselves. They arc through the wall, and the heat of the static discharge burns the plastic and puts a hole in it. This is what a pinhole leak looks like if you did a sectional and electron microscope. This is where you see the channel coming through, where it is arced through the pipe wall and it kind of filigrees out. It looks like a lightning bolt. Now, the Gas Research Institute has found that pinholing can occur in any kind of gas operation. In the normal operation of gas transport, pinholes can be created. And if you've experienced, sometimes people say to me, well, I'm not sure if I have static in my system. If you've ever had a pinhole leak, you're going to find that that's prima facie evidence that you have static in your system. We're going to be talking about the levels of these voltages in a minute. Now, once again, we have to make sure we're using the same terminology, that we understand. When I use terms, we're all on the same wavelength. And I want to explain what static electricity is. Sometimes when people talk about static electricity, they think it's kind of an inferior electricity. You know, the real electricity is the stuff coming out of this wall down here that's powering this laptop and broadcasting this webinar. Well, electricity is electricity. Static electricity is electricity that is on a surface of a material that can't move, and therefore it's static. It's electricity that finds itself on a material that is not an electrical conductor. Now, I'm down here in Boca Raton, Florida, and up in Juno Beach, Florida, Florida Power and Light has a generator. And that generator creates all these excess electrons. And what they do is they take these excess electrons and they deposit them on copper wire. Now, copper in and of itself, in its physical nature, has the ability to conduct electrons. Electrons run smoothly through that material. And so when FP&L deposits those electrons on that copper wire, what happens is the copper allows the flow, so they direct that to the user, and that current of electricity, that movement electricity, is delivered to my outlet down there. But now let's just take the opposite. Let's say FP&L did the same thing at that generating plant. They created this excess pile of electrons, but instead of depositing it on copper, they deposited it on polyethylene. Well, polyethylene, by its inherent nature, resists the movement or current of electricity through the material. It's like it says, you know, puts its hands up and says, no, you can't move. It's just inherent in there. So if FP&L deposited those electrons on that polyethylene, those electrons would just sit there. They'd be static. And so they wouldn't move. And so we call electricity that is on a material that won't move static, not because it's not electricity. Electricity is electricity. Electricity is energy. But it's static because it resides on a surface that it cannot move on. It doesn't conduct on. Well, how's static electricity created? Well, in most cases, it's caused by friction. When you have the movement of one material, which is an electrical insulator, rubbing against another, the mechanical shearing action of the passage of one against the other mechanically shears off an electron. The electron there's not enough strength in the atom to hold all the electrons in, and you overcome that force, and all of a sudden these electrons get sheared and they come apart. And so they have a tendency to accumulate at random places on surface since they've been lost and removed from their original atom. And so they accumulate in certain surfaces, but it's caused by friction, by the movement of gas. Well, in our case, in the natural gas distribution business, it's caused by the movement of methane, which is an electrical insulator, against the inside of a polyethylene pipe, which is an electrical insulator. And so all the static starts on the inside of the pipe because that's where the friction is. That's where it starts originally to build up. Now, your problem of how to solve this is because Mother Nature doesn't like electrical imbalances. The natural world is designed to be at electrical neutrality. So what happens is, like in this picture on the right, in the summertime, then the ground heats up the air and the air goes up and then it cools off and it comes down and it goes up and it goes down. The friction of that air going up and down creates static electricity, and that static electricity gets so high that it wants to neutralize itself and it arcs the ground, and you get this lightning bolt like you see in this photo on the right. Well, the same thing occurs inside your pipe. If the static charge gets high enough inside that polyethylene pipe, finally, even though polyethylene can resist static electricity to a certain point, it can't it cannot resist it infinitely. And there's a point where it breaks down. And so the electrical charge inside that pipe arcs through the wall to go outside to neutralize itself in the ground it's buried in. And as you see here on the left, the photo I showed you before, it's like a miniature lightning bolt. That's really what it is. You have a miniature lightning bolt going from the inside of the pipe to the outside of the pipe. And in doing so, it burns a hole. So given the fact that static originates inside the pipe from the passage of gas, these charges don't go away, that those electrons just sit there. Mother Nature wants to go to electrical neutrality. So what happens when static electricity builds up inside a buried pipe? You get a hole. Okay, now we're going to go through, this is the beginning of 4 failure analysis. Now, most of the time when people think about static electricity in polypipe, they think about ignitions because that's the most demonstrative incident of static electricity around leaking natural gas. But this paper that I'm showing you here was written for the Plastic Pipe Symposium back in, I think, around 1985, if I remember right. And it was written by a guy who's in the training department at Mountain Fuel Supply, which is now Questar, which is now Dominion. And he wrote it because what was happening, this is the first paper about static electricity in polyethylene pipe, and it was not about ignitions. It was about pinholing. He found that what happened is when they were doing squeeze off and they'd be checking after the squeeze off, they found there were pinhole leaks around where there was squeeze off. And they started to investigate and find that many times when they did squeeze off, they were creating pinholes. And so what they did is they sent this pipe, it was 1 1/4 Aldil MDPE pipe. They sent it to the DuPont lab for testing. And what DuPont came back and said was that the pipe was manufactured to spec. There wasn't anything wrong with the pipe, but the cause of the internal static arcing through the pipe wall and creating the leak through the pipe wall was static electricity. The second report here was with United Cities Gas. It's now Atmos Energy in Tennessee. They were having leaks in 1/2-inch Plexco PE pipe. So what they did is they sent it to GRI, and the GRI in turn sent it to Battelle Labs. Battelle Labs went through and tested the pipe, and they said they determined that the cause was material breakdown due to a static electricity field inside the pipe. Now, this third failure analysis was some 1-inch performance MDPE pipe. And I wrote it with the standard engineers at Memphis Light Gas and Water, Ray Ward. He's since retired. He's been retired about 4 or 5 years now. And it's about this pipe on the left side. And let me tell you the story about it. What had happened is Memphis had contracted with a contractor to install this 1-inch MDPE service line. The contractor came in, installed the line, pressure tested the line. The line passed pressure test. Memphis signed off. Then the contractor went away. Everything was fine. Memphis came back, installed the service, purged the line, and when they pressure tested the line, it failed pressure test. Well, they were going to go back to the contractor and back charge the contractor saying, hey, faulty installation, it's got pinholes in it. The contractor rightfully asked the question, how could it have passed pressure test before if it was bad? And so what they did is they pulled this service line out of the ground and they did a hydrostatic test on it. And this piece of pipe, Ray Ward told me, when they did a hydrostatic test on the ground, it looked like one of those hoses, those lawn watering hoses you go to buy at a do-it-yourself store. It's got 100 little holes in it to irrigate the lawn. This pipe had hundreds of holes in it, caused by the friction of the static when they purged the line. It created all these pinholes in this line. So this was the paper that was presented to the Plastic Fuel Gas Pipe Symposium about this particular pipe. And what happened is it was sent to Performance Lab. Performance Lab looked at it. They said it was due to static electricity inside the pipe. They confirmed that. Last one here was in Connecticut. It was a 4-inch IPS PE medium density pipe. And once again, they were having pinhole leaks in it. They sent this one off to GTI labs. GTI labs tested the lab, and they determined that the cause was static discharge failure inside the pipe. Now, you have 4 failure analysis here, and there's some commonality that you see in here. In the first one, in Mountain Fuel, that went to DuPont lab. United Cities went to Patel lab. Memphis went to Performance Pipe Labs. Connecticut went to GRI's lab. All 4 different labs, all the same conclusion. Static electricity in the pipe caused the pinhole leaks. You had different material. You had Aldel, you had Plexco, you had Performance. Again, different materials, same thing, static electricity. It wasn't confined to one manufacturer. You had different US locations. Mountain was in Salt Lake City. United Cities is in Nashville. Memphis is in Memphis, Tennessee. Connecticut was up near New Haven, Connecticut. All across the United States, static electricity in the pipe. It was their same conclusion on all 4 different labs, static electricity in the pipe. And they said it was not a manufacturing defect. In other words, there were no holes in the pipe at the time of manufacture or no out of spec dimensions. When there is a defect in the pipe, first of all, it would have failed inspection when they first installed it, when they pressure tested it. It was a manufacturing defect. But secondly, manufacturing defects will not have the telltale marks that a pinhole does. The pinhole shows, as you said, it's a filigree. It looks like a lightning bolt going out. Manufacturing defects, it'll just have a hole or something like that in it. It won't have that filigree and pattern. And plus, you'll see black. Again, you can't see it with a visual eye, but if you go under a microscope, you will see a blackened area where that pinhole is burned. So they said it was not a manufacturing defect that caused these holes. Now, we're going to go to the third thing is in the States here, PHMSA has jurisdiction over PE gas service lines. And what they did in 2015, they proposed a rule that would not allow regrind in PE fuel gas pipe. Now, the reason I want to go through this is the reasoning and the logic that they laid out in it, because it gives you further understanding of pinholes and polyethylene pipe. In Canada, for at least 5 years now, you've not allowed regrind in pipe. Now, maybe some of you know if it was always that way with your PE fuel gas pipe, or at some place in the usage of PE pipe, they made that rule. And if anybody knows when that was, if you chat that in, I'd appreciate it, because that'll have some bearing, as you'll see, in what we're going to talk about. But I want you to see their thoughts. What they did is PHMSA said, we do not want regrind used in the creation and the manufacture of PE fuel gas pipe. Regrind is material that is left over from a run of making pipe. What happens is when they make polyethylene pipe, they make pipe like your wife makes a cake. She has a recipe. She gets out a recipe. She gets a big bowl and she pours in flour, then butter, then sugar, vanilla, baking soda. She mixes it all up and puts it in the oven and bakes the cake. Well, pipe manufacturers do the same thing. They get a big hopper and they start to pour in their virgin polyethylene medium density resin, which is kind of a milky clear color. Then they'll put some yellow coloring in it. And then they'll put some UV stable inhibitor and they'll put a stabilizer in it. Whatever their particular recipe is, they're all fairly close, but they have a recipe. So what they'll do then is they start to mix all this up and they heat it up and it turns into kind of a sticky goo. And then they start to extrude it through an extruding machine to make the pipe. Now, when they start that process, you know, common sense tells you that the first bits of pipe that go through there won't be to spec. Maybe they may be a little oval, the walls may be too thin, you know, something like that, until they get the machine flowing and the melted resin, you know, going. So what happens is when they start that process, the material in the pipe that initially comes out that's not to physical spec. Remember, the recipe is all the same. I mean, the chemical formulation is the same from the beginning of the run to the end, but the beginning of the run, the physical characteristics of the pipe may not be uniform. And so they cut that off, set it aside, and then they start extruding the material, the pipe that meets spec, and they roll it up and they finish. And when they're done, they may have a little bit left over that's out of spec as the machine ran off. They cut that off and they set that aside. The next time they make that same kind of pipe, what they do is when they make their big vat, the stuff that was left over, the plastic that was left over that was not to physical spec, it was to chemical spec, but not physical spec, they chop that up, throw that in the mix master and re-extrude it. Well, PHMSA said, we don't want you to do that. And that's what the rule was all about. And I'm sure the reasoning up and for Canada and the reason they don't have regrind in polyethylene pipe is the same. And I want to take you through the reasoning. And what they did is PHMSA got comments from all the distributors, AGA and all the distributors, from the pipe manufacturers, from third parties and all that. And they all basically, put in their 2 cents worth. And PHMSA still ruled that they do not want regrind in pipe. And so I'm sure that the thought pattern of PHMSA is the same for the Canadian authorities. And here's the research that PHMSA used. They used analysis of microscopic leaks in polyethylene gas distribution pipe that was done by the Electric Power Research Institute. They did electrochemical treeing in cable. Remember when I showed you that picture of that polyethylene pipe that had pinhole? It looks like a filigree of trees. It's like a lightning bolt or a tree. Electrochemical treeing in cable. Deterioration of water immersed polyethylene coated wire by treeing, once again, by the IEEE, International Electrical Engineers. And so what they did is their reason, here's what they said. They said, these reports indicate that regrind work could potentially be an issue of concern, particularly through the breakdown of dielectric properties, development of pinhole leaks and static discharge. In other words, PHMSA was saying that they're looking at the problem. They say the problem is static electricity, and rework can make it more prone for static electricity to put holes in it. And that is most likely the reason why authorities in Canada did the same thing, that they prohibited the use of regrind. So restating what PHMSA down here in the States said is there's an ongoing problem with pinhole leaks in PE, which they want to prevent, and regrind and rework could be contributing to this. And that's the reason they did the rule. They're telegraphing to the industry they don't want pinhole leaks down here in the States. And they implied that in the handling of the regrind, contaminants could get in there in the handling of it, regrinding it up and then putting it back in there, that could be the cause. Now, most of the pipe manufacturers said, we don't think it's an issue, really. There's not that much contaminant, but that doesn't matter. They got all the comments, and most of the manufacturers in the States were allowing regrind. We're putting regrind in, 1 or 2 didn't, but they said, we really don't think it's going to make an issue. But PHMSA down here said, we believe that it is contributing to pinhole leaks, and we don't want pinhole leaks in pipe. It's important to remember, though, in all this, that the common denominator in all of this has been static electricity. That's the root cause. What they're doing is, by not having regrind, they're hoping that it kind of raises the threshold where a pinhole occurs, but it's caused by static electricity. It's not caused by regrind. Regrind can be a contributing factor, but the root cause is static electricity. Now, there's a couple problems with this rule, and it would be the same up in Canada. Probably down here, if that is true, if they say that the contaminants in regrind contribute to pinhole creation, you got a problem is that all this legacy pipe is more susceptible to pinholes, and you're going to get pinhole leaks. And it's the same in Canada. If there was a period where you had regrind in that pipe, it may mean that legacy pipe has a higher propensity to pinhole. The contaminants allow pinhole creation. But the second thing is, down here in Florida, down here in the States, there's 912,000 miles of PE service pipe already in the ground that had regrind in it. So you got to deal with this problem. The same with you. If in Canada there was a time, maybe in 2010 or something, where they passed the rule that there's no regrind, you got all that legacy pipe in the ground that has regrind in it if regrind is an issue. But the most important thing is this third thing, and that's this. No regrind in pipe doesn't mean it won't pinhole. Every pipe will pinhole if the voltage gets high enough, because there is a certain limit to how much voltage a piece of pipe can take. If you take an MDPE pipe and pressure it to 125 pounds, it's going to be okay. Then you start to move it to 150, it may start to deform a little bit, and any weak spots or little variations in the wall thickness will start to appear. You start to go to 200, and it's eventually going to fail. Now, there's nothing wrong with the PE, but there's a physical limit to how much pressure that PE pipe wall can take. Well, it's the same thing electrically. There's a certain limit to how much that polyethylene can put its hands up and say, no, I can resist this electricity. I can resist this electricity. Finally, it says, I can't resist it anymore, and it arcs through. So even 100% virgin resin, MDPE, it's going to pinhole if the internal voltage exceeds 510 volts per thousandth of an inch of wall thickness. Now, what PHMSA was saying and what the Canadian regulators are saying when they say no regrind is that threshold may be lowered if you have contaminants in there that with a dielectric less than pipe material. Let's say, for instance, in the regrind, some dirt got in. Well, that little particle of dirt embedded in that wall has more electrical conducting capacity than MDPE. So if the static builds up, it will fail by going through that little piece of dirt, because that little piece of dirt reduces the conductivity at that point. So that's the reason that they say that contaminant would lower the threshold, but it doesn't mean that it won't pinhole. It will pinhole when the voltage gets enough, and you can calculate this. Now, in MDPE yellow gas pipe, the dielectric, or the insulating, or its electrical resisting capacity, is about 510 volts per thousandth of an inch. It varies a little bit between manufacturers of resin, but it's pretty close to that. So if you've got 1 inch yellow gas pipe, it's got a nominal wall of 120 thousandths of an inch. If you multiply 120 mils times 510, it's saying if the voltage inside gets to 62,200 volts, you're going to get a pinhole. Doesn't matter whether there's regrind or not, it's going to break down at that voltage. Now, to put that in perspective, if you have leaking gas and static electricity present, you could have an arc of static electricity. That does not mean it's going to ignite the gas. The voltage to ignite leaking gas, a gaseous mixture, must be at least 3,000 volts, because if you don't have 3,000 volts, the spark does not create enough heat to ignite the methane. A 3,000 volt spark creates 1,100 degrees of Fahrenheit of heat. That will start the reaction. That'll start the oxidation. 2,000 volts, it's not high enough. So this gives you an idea of the magnitude of voltages you're dealing with. I remember I told you there was a 4-inch pipe there that up in Connecticut that had a pinhole leak in it. You're talking of voltages in the magnitude of 200,000 volts. I had a customer at a gas well in the Permian Basin. They usually use 4-inch poly gathering pipe out in the gas fields. They had pinholes that burned away the pipe and caused a well fire. 4-inch pipe, you're talking like 200,000 volts. Now, logically though, if you follow this logic through, you're going to see a pattern here. The smaller the pipe, the thinner the wall, the lower the voltage is necessary to put a pinhole in it. Therefore, you're going to see your pinholes in polyethylene service lines first. So for instance, a 1/2-inch polyethylene gas service line, the nominal wall thickness is 90 thousandths. 90 times 510, 45,900. So you can see that as the voltage the static starts to arise in the system, the first place you're going to start to experience it is going to be in your smaller service lines, because it'll hit the threshold of the dielectric constant first in a smaller diameter pipe. Now, as we have dealt with customers on this, we found patterns emerging here. Most pinholes occur in 1 inch or smaller plastic service lines. Again, I just took you through the math. You can see the smaller the pipe, the more susceptible it is to static in the pipe. There's no pattern in the number of pinholes in the pipe. I've seen pipes where they have a service line, it'll have, 1, 2, 3, 4, 5 holes. Again, when the static conditions are right and the static builds up inside that pipe and it arcs through, it's going to arc through in different places in that pipe wherever the voltage hits the maximum of the dielectric of the polyethylene. I've only seen it in high density and medium density PE pipe, not in PVC. Somebody asked me, do you find that the dielectric constant is higher for MDPE? You would think high density polyethylene would have a higher insulating or dielectric constant than medium density. That's what I thought when somebody first asked me the question. And when I looked, I was surprised there's not that much difference. It really is very small. Maybe a difference like 530 versus 510, not significant at all, which was kind of a surprise. As you saw in those failure analysis, this was not limited to one brand of pipe. We had Plexco, DuPont, Performance, all of them. It's not a function of bad manufacturing. Pinholes cluster in groups and lines in geographical areas. I don't know why. It is something in the characteristics of the ground, the gas or something, but usually they congregate in areas. We're having a problem in southern Indiana, southern Ohio, northwest Kentucky. Benton, Kentucky is up in the northwest corner of Kentucky. We've had that problem in that area. Fredericksburg, Virginia, you see in the Nashville area, they had that. But if you find pinholes in pipes in a certain area, you got more. You just they haven't come up on your leak survey yet. They tend to congregate in geographical areas, and they're going to continue. The conditions are such that when pinholes start, you may find they go down a little bit. There may be some seasonality to it, but you're going to find they're going to continue. They're not going to go away unless you intervene. This picture was sent to me by Fire Findings Newsletter. Fire Findings Newsletter is a forensic fire investigators newsletter circulated around the states. And when fire investigators go look for causes of fire, they share what they found to help prevent it. And I got this from them because they were getting fires at gas meters and they could not find the ignition source. They couldn't figure out where it was coming from. And they said, could it be pinholes in service lines where the gas is pooling and igniting around the meter? Sure can, sure can. Pinholes, the problem with pinholes, they will keep accumulating. They will not stop. You can replace the pipe, but you're not solving the problem. It's not a materials failure, it's a static problem. In the States here, and I'm assuming it's going to be the same up there, that if you've got something that's causing leaks, you've got to deal with it. Down in the States, they're required to have a leak management plan to do that. Now, what this means is then, if it's true that internal pipe static is the cause of pinholes, well, then it follows, if we suppress internal pipe static, that should stop pinhole creation. That's the logic of it. Whoops, oh dear. Excuse me. I apologize. This is a city of Benton. Remember I was telling you there was a problem with pinholes in the northwest area of Kentucky. This is a municipality up in the northwest area, and they were having problems with pinhole leaks in their poly service lines. They have about, at the time, I think their number of services increased. They have about 7,033 services, 317 miles of mains, a pipe. And what happened is, this is 7 years of their leak surveys. They did a 1/3 survey every year. And this is the leaks survey as they shown it. And what you find is, first of all, you notice that generally the smaller the diameter of the pipe, the more of those pipe you have of pinhole leaks. Makes sense. We've gone through the math. That makes sense. That's logical. They found it in all brands of material. They had it in orange, Aldo, yellow pipe. Again, it's not the brand. It's the dielectric. It's the dielectric strength of the polyethylene. And they averaged about 11 leaks a year. So they came to us and they said, would you put in we want to put your internal static suppression cartridges in our system to reduce the number of pinhole leaks. So in 2013 and 2014, we put in 2 of our cartridges. They are supplied, they have 2 delivery points, 2 gate stations. One is a 3-inch, one is a 4-inch. So what we did is we put a housing at those gate stations, and we put those housing contain our cartridge. On the left-hand side, you see a cutaway of the housing, which is holding our static suppression cartridge. And what happens is gas passes through our cartridge. It's not a filter, but what happens is when it passes around our treated core, we dissipate the static downstream, the interior static creation downstream to burner tip. So they had 317 miles of pipe, and we put 2 of these at their gate stations. This is the leak survey. I haven't gotten their leak surveys for 20 yet, but this is the leak surveys from the following 6 years after they put our static suppression cartridges in. That was the only change they made to the system. All they did is put our 2 cartridges in. You see a drastic reduction in pinhole leaks. Instead of averaging 11 leaks per year, they're averaging 1.4. Now, some of these can be legacy leaks because they're kind of hard to detect depending on soil conditions. But it's a statistically significant difference. It's an 88 statistical difference, 1.4 leaks in here. It made a huge difference in the repair cost. You know, whenever you start to dig up a line and replace it, you run the risk of creating another problem when you invade the ground to touch a pipe. But basically what this is, it shows that all research, the research is right, that internal static causes pinhole leaks. And therefore, if you want to stop pinhole leaks, and stop pinhole leak creation, you got to eliminate the interior static inside the pipe. And you put interior static suppression upstream. And so basically what it involves, what this Benton did is you can put our static suppression cartridges anywhere in the system. They wanted to put it up at their gate station to treat their whole system. But I have a customer in Indiana, Southern Indiana, they had a master meter and they were getting pinhole leaks in their master meter system. So what they did is they put our static suppression just upstream where the master meter was. Problem gone. They didn't have to treat their whole system. They just treated a section of their system where they were experiencing that problem. Some people want to put it up at their gate station. The United Cities case study, the failure analysis I showed you, that was taken over by Atmos, and the city was Shelbyville, Tennessee. And they put just our cartridge just in the section feeding that city to stop the problem. They've stopped the problem. So it can be put any place you want. It's really up to you. All you have to do is you have to pipe in a housing to hold our cartridge so that the gas can pass through our cartridge. And everywhere downstream where the gas is passed through our cartridge, we prevent the buildup downstream. But you have to understand, if you have backfed systems or secondary feeds that aren't treated with Ionix, that untreated gas lowers and dilutes the effect of the gas that's going through the Ionix static suppressor. They're sized by pipe size and pressure. So for instance, for Benton, the city of Benton, it was a 3-inch feed and it was 280 pounds, I think. So what we do, our cartridges are sized by the diameter of the pipe it's going on and by the pressure at that point of installation. Because the bigger the pipe, the more gas, the more we have to treat. The pipe of 3-inch at 280 or a pipe with 2-inch, 3-inch at 1480, 1480 has more gas, so the cartridge has to be different to treat the higher volume of gas. So what we do is they're basically treating the volume of gas, and we determine that by the pipe size and the pressure at point of installation. The only maintenance is you just change a cartridge once a year. What we do with our customers is we call them up, say it's time to replace it. We send them the new cartridge ahead of time. And when they're ready, when they say it's okay, we send them the new cartridge. They take the old cartridge out, send that back, and put the new one in at the same time. It works automatically. When gas passes through it, it automatically dissipates the static and treats the gas as it goes through. So with that, we are done. we have covered everything, and I'll be happy to answer any questions that you have about pinholes and polypipe. And Mr. Dillon, it's to you.
Yes, Dirk. So question for you. How do you determine where and how many cartridges are needed?
Every system is, I tell people two things I know for certain. I know for certain that everybody has static in the gas system, and I know for certain that everybody's system is different. So basically, what it starts off by somebody saying, we're having a static problem, and they describe the system. They say, okay, here's how it's fed, here's where our problem is, and then we give them options. Do you want to just treat a little regional area, or do you want to just treat the whole thing? Because what happens is, if you get rid of the static in the whole system, you not only, these people, it not only solves the pinhole problem, but it suppresses static that causes leaks. It suppresses static that causes shocks. And it also suppresses static that can burn out solid state materials, meters and any kind of electronics hung on system. So getting to your question then, it really is up to the customer where they want to install it. They just have to tell us. Like I said, I've had a customer that if he said, I have a master meter and I want to solve the problem here. Okay. The outside diameter of the downstream size of the pipe upstream from the master meter was 3 inches, and it was 150 pounds. So we did the housing and the cartridge for a 3-inch, 100-pound at that point. If you want, I've got some customers that they want at the gate station. And so that's maybe 4-inch at 1,480 pounds. So we size it based on where they want to put it in, Mike.
Okay, thanks. We've got another question here, Dirk. How does the ISSC work? It would seem it wouldn't stop the gas rubbing against the PE problem downstream. Does it countercharge the gas or something else?
No. What happens is you cannot stop physics. What happens is when those electrons get knocked off, they become stray electrons. Now, here's what's happening. If you think of it on an atomic level, there's atoms running around there that are missing an electron, and there's electrons that don't have a home. What we do is we make the gas electrically conductive, so stray electrons find their way back and reconnect. When they've been knocked off, we give them an electrical path to go back and rejoin molecules that are missing one. That's what they want. Essentially, we neutralize it. We allow the electron to find its way home. Okay.
Another question, is the likelihood of the pinhole leaks related to gas pressure and or velocity?
You know, I think it's more velocity, but I don't know that there's been any studies done for that. You know, I've had, I mean, I got like that master meter system. That master meter system, you know, that's pretty close to delivery. Yeah, well, it's, you know, delivery. And that's not at any high pressures, and yet they were having pinhole problems there. It probably and in the same way in service lines, most of these service lines, you're down to what, 20 pounds, depending on where you are, 10 pounds, 20 pounds, and they're getting pinholes there. So there hasn't been any study done on it. Surely velocity is a matter, but there's nothing you can do about that. I mean, you know, it's velocity.
So in your experience, Dirk, have you seen any patterns that are useful, you know, pipe vintage, soil conditions that help us identify areas of higher risk versus others?
No, there's been nothing done in that area. No research that I'm aware of. And
so we're just chasing leaks, basically.
I'm sorry?
Just chasing leaks.
It's chasing leaks. It's really just chasing leaks because you have no idea ahead of time what's going to cause this problem. But once it's there, whatever the conditions are, they're there.
Okay.
Like I said, you'll find it in geographical areas. It's unusual that you find just one. There's others.
Hold on 1 second. Dirk, can you hear me okay?
I can indeed. Whoop.
Can you? Oh, thanks.
Whoop, 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 whoop.
So we've got another one. If we currently do not have any static pinhole leaks within our system, are we able to measure internal static electricity to potentially prevent from any from occurring? Good question.
We have a electrostatic locator emitter. The problem with static is, you know, in my experience, I remember one time I was asked to go take a look at a system, and they at Benton, it was Benton, Kentucky. They were having at Pinholes. So I went up there, and what they did is said, okay, let's go find static. So I got my meter out. They went to a regulator station. They took a stop off, and they just vented methane out at like 99 pounds and 5-foot section of poly pipe, right? I'm thinking, oh, this will be easy. I'll find static in this. I run the meter on it, no static, none. We do that at another regulator station, none. I'm going, holy moly, these guys are going to think I'm nuts. And Kelly said, well, I have a friend of mine and he let me trench his service line to his house. So well, let's see if we can measure some static there. So it's a 1/2-inch line going, and it's April, right? April. I mean, there's in Tennessee or Kentucky, it's spring. So I go to there and I'm thinking this trip was a waste of time. I put my meter down on this 1/2-inch service line going into the house. I pin the meter. The problem is you never know where it is. You could, you know, I mean, in places I've thought for sure I'd have static, I don't get it. Places where I don't think I'm going to have static, I got it. And that's the problem of trying to find it. The static problem you have, it's the evidence of it. You can't find it when you have an ignition, or you have an unexplained ignition of leaking gas, or you have a pinhole. That's when you know for certain you got static in your system. You have static in your system. Everybody has static with their poly pipe, and then metal pipe too. But poly is of course more important because plastic's an electrical insulator. But usually it's when you have a overt event caused by static that you know that you have static in the system. Chasing static down in a system with a meter is hard, I found. Gotcha.
Okay, to our guests, thank you. Is there any other questions out there before we conclude? Dirk, is there anything you'd like to say in closing?
Well, I just want to thank you all for your interest in this. CR Wall's been our distributor in Canada for a number of years, and they've represented us very well. And if you do have any questions, we work with them on a lot of different things, and I'm sure together we can solve any pinhole issues or static electricity issues in your system that you have. And I want to thank you all for coming, and thank you, CR Wall, for taking the time and the effort to sponsor this.
Good, Dirk, thank you. Yeah, on behalf of CR Wall, thank you to all of you for joining us today. We appreciate you supporting this and your interest in the subject. And please reach out to any of your CR Wall Foothills colleagues, and we'll certainly help you answer any questions and help you with your static issues. With that, I would like to conclude. Thank you, Dirk. Special thanks to you. Always enjoy our talks.
I'm going to the beach now, Mike. I'm going to the beach.
Yeah, head to the beach, man. Yep. Thanks, guys. All the best.
Thank you. Have a nice day.
Take care. Bye-bye.
Bye.